and welcome to our digital walkthrough of the circuitry notes. So, I just want to emphasize again that this is a more difficult part of physics that we've gotten into. A lot of these things are harder for us to see. That's fine. If you have questions, please email me. There's a lot of little parts of circuitry that can be a little counterintuitive and odd at first glance, but there is reasoning behind it. So if you have questions, if I don't explain something well enough, please email me. So, circuitry. Not many of us will have probably seen the circuitry, but circuitry is in all of our electronic devices. Our computer screens, our TVs, our cell phones, our computers, our laptops, everything. Everything we have that uses any kind of electricity has circuitry built into it or uses circuitry. So what is circuitry? It's essentially the pathways that allow electricity to flow through our electronics, controls where it goes, and lets it essentially controls what it does. There's a bunch of different parts of these circuitries, and there's something we have called circuit diagrams that are shown here that make it a little simpler for us to see what's going on and determine the path of things. So parts that we have the battery. Battery is usually displayed either by a physical battery in some drawings, or sometimes it'll be these weird bars, like shorter and longer, representing positive and negative sides. Negative side being the shorter one, positive side being the longer one. That's one way that we can see battery shown. Wires, it's just lines. Resistors, next up over here, are these squiggly lines up and down like this. That is a resistor, which we will get into what all of these are as we go forward. Bulbs, light bulbs, are usually shown as another type of resistor, or they're a stand-in for a load. Junctions is just a branching path away from the wires. When a wire splits off into two or more directions, that's a junction. Capacitors we don't get into too much. Capacitors essentially store charge. They kind of act as like a buffer. So if for whatever reason a little bit of the circuitry fails briefly, the whole thing doesn't completely shut down because there's this buffer built in. And finally, switches. These are things like light switches, anything else to turn the circuit on or off, or turn certain paths on or off. Just as a quick example of a load, since I talked about light bulbs a little bit, the bulb of a flashlight is a type of load. That is where essentially work is being done in the circuit to do something. Either to make lights work, to make a radio turn on, have your computer screen give off light, show pictures, things like that. Anywhere where work is being done in a circuit is called the load. So let's go into a couple of these different parts and the main two types of circuits we have. First off, we have the junction law. In essence, all this is saying is whenever you have an intersection, I'll draw one here as well, any current flowing in to that junction has to be flowing out as well, the total. If I have 10 flowing into this junction right here, I have 8, we'll say, going this way, there'd have to be 2 going this way. Whatever flows in has to come back out. And likewise, if I were to all the way over here have these come back together, and we'll draw an arrow this way, we have the second junction, we would have 8 flowing in here, we would have 2 flowing in here. That would mean we'd have to have 10 flowing out of this part of the junction. Anything flowing in has to flow out, and it will eventually recombine near the end of the circuit, or some place in the middle, depends where. Anything flowing in has to flow out. That's all it is. All right, next up, two main types of circuits that we have. We have something called series circuits and something called parallel circuits. This essentially just describes the layout of the circuit. If the circuit is in series, it means everything is in a line, one right after the other, after the other, after the other. As we can see in this left-hand picture here, both of our loads, both of our light bulbs here are in series. They're in a straight line. They're not branching off into different paths. However, for parallel circuits, this is when we have different separate pathways. You can think of these as separate streets if we were in a city. Certain streets are parallel to one another. They're entirely separate from one another, but they flow in the same direction. That's what we have going on over here. We have a junction right here. We are flowing from the battery into a junction, leading us to two separate pathways, two separate parallel parts of the circuit. And we'll get into these in more detail. Series is one right after the other. Parallel is splitting off into two or more separate pathways. So we're going to start with series circuits. Series circuits are the most straightforward of the two. Basically, just in a series circuit, if we're looking at current, it's going to be the same everywhere. The current here right after the battery will be the same as up here, which will be the same as after this resistor, which is after this resistor, and at the bottom here. At every single part along this way, the current will be the same. Again, if we go back to a water analogy, if you have water flowing through a pipe, the water, assuming there's no leaks or anything, the water flowing in one side of that pipe will be the same amount of water flowing at the end of that pipe. Water doesn't magically appear or disappear in the middle of a pipe. It's the same the entire way. And this will potentially cause a little bit of confusion later on, but we will get into that. Okay? Key takeaway, the current at every single part in a series circuit is the same. It never changes. If I start with 10 amps of, if I start with 10 amps here of current, I'm going to have 10 amps over here as well. And I will also have 10 amps down here at the bottom. It's the same everywhere. And as always, this is shown by the symbol I for current. So, am I missing anything? I am not. Alright, next up, just another quick diagram of this, of a series circuit. We have a bunch of light bulbs in series. The current that goes through one light bulb will also go through the other light bulbs. And this does have some ramifications when we're talking about how bright light bulbs would be, how much power is able to go to those. And we'll get into those more when we talk about parallel circuits. The differences essentially between series and parallel. This is just a quick example of that. Next up, resistors. We've talked about current, now we're going to talk about resistors a little bit. Because there is a difference between resistors in series, that we're talking about right now, and resistors that would be in parallel. And both of those will end up being on your equation sheet, so don't worry about that. So, when we have resistors in series, one right after the other, after the other, after the other, they essentially act as a single resistor. So if we remember back to Ohm's law, V equals I, R, if we know the current and we know the resistor, we can find out how much voltage, how much electrical energy it takes to get across that resistor. That's what Ohm's law is telling us. If we have a bunch, one right after the other, we can just treat it as a single one. So, for example, if this one was 5 ohms, this one was 10 ohms, and we'll say this one was, I don't know, also 5 ohms. If they're all in series like that, we can just add them together. So, the total result, essentially, the combined resistor, we could just replace it with one that was 20 ohms. Both of these circuits are identical. Whether or not we have 3 like that or 1 right here, it's the same total resistance from the top to the bottom of 20 ohms. Because they are in series, because they're one right after the other, we can treat them the same way. So whenever you have resistors that are in series, you can just add them up together and replace them with a single resistor of that same total, and it will be the same exact thing. Just another quick example, when we have a bunch of light bulbs in series, if each one has a 1 ohm resistance for that light bulb, for that load, we can just add them all up. We get a total of 3. We could replace those 3 light bulbs, which is a single light bulb of 3 ohms, and the circuit would behave exactly the same way. Nothing would change. Next up, voltage. We've talked about current, we've talked about resistors, now we're going to talk about voltage. Same thing. If we are working in series, we can just add up the different voltage drops, and it will act as a single voltage drop. So, what do I mean by a voltage drop? So, essentially what voltage is, it's a measure of the energy within a circuit. We can kind of compare this to potential energy, gravitational potential energy, since we're familiar with that. If I were to have a cliff here, we'll draw one of these in here, like this. Let's say this cliff is 3 meters high. We'll say that. Once you're at the top of this cliff up here, you're going to have a certain amount of gravitational potential energy than if you were at the bottom. Now, if I were to instead go off to the side, maybe go down a little bit to here, go down a little bit to here again, go down a little bit to here again, and then get to the bottom here, the potential energies, if you added up all these drops together of a 1 meter drop, a 1 meter drop, and a 1 meter drop like this, oh, I put one too many. One too many drops in. Like that. So essentially, if you're adding up all these different potential energies at 1 meter high and then another meter high and then another meter high, it's the same as if you were just adding them all up together and treating them as one giant cliff. It's the same thing with circuits and voltage. It's the amount of essential energy you're losing or using to go across a load. So if we go across this first light bulb, let's say we use up 1 volt, then a second volt, then a third volt as we get all the way to the bottom, that battery would be providing 3 volts, a 3-volt potential difference, essentially. So if we have a battery of 15 volts, we'll just say it has 15, the total drop from the start of the circuit, right here at the positive terminal, all the way down to this negative terminal here at the end, going through the entire circuit, you would need to have a 15-volt drop. You would need to use all that voltage going from the beginning to the end. And that can be split up however it needs to be. This one we could just say is 13, this one then would be 1, and this would be 1. This can be split up however, it depends on Ohm's law. And remember Ohm's law again, which would be V equals I R. The voltage drop at each individual light bulb will depend on how much resistance it has. Because remember, when we're in series, this current is always the same. This is how we're going to determine each of those different voltage drops, is by using Ohm's law, assuming that's what we're looking for. So remember, the voltage drop from the beginning to the end has to be equal to whatever the voltage of the battery is. So if we have a voltage of 3 for the battery, the total drop across the entire circuit needs to be 3. So this is just, again, basically repeating what I just said. And same thing here. So, the total voltage dropped across the entire circuit is going to equal whatever the voltage of that battery is in a series circuit. This is something called Kirchhoff's loop rule. Essentially, all Kirchhoff's loop rule is saying is that the total energy you expend through a circuit is then gained or provided by the battery. So if it takes a certain amount of energy, a certain amount of volts to go across the entire circuit, that's how much that battery will be providing. Resistors in series, we already covered. You just add them up together and you get an equivalent resistance. So, brightnesses. So here's the thing. When we only have one light bulb here, let's say, again, just for sake of simplicity, we have 3 volts here. Well, if we're using 3 volts, if that's essentially our electric energy, and there's only one resistor there, one load, all of that energy can flow into that one light bulb and it will be really bright. Now when we go in and add in a second battery now, or not a second battery, a second bulb here, well, now we're splitting that 3 volts across 2 separate light bulbs. Instead of a 3-volt light bulb now getting 3 volts of power, now it's only getting 1.5 volts. Each one's only getting 1.5. We add a third bulb, now each one's only getting 1 volt. Similar to wattage. The higher the wattage of a bulb, the more power is required for that bulb. That's essentially what we're seeing here with these voltages. When we split that out, each one has a smaller drop. Each one's getting less of the overall pie, essentially. Each one's getting less of the total. So that bulb is going to dim. So there is a way we can address that, and it's using parallel circuits, which we'll get into. One other quick note, specifically with light bulbs here. If you've ever had a Christmas tree or something like that, whenever one of the bulbs goes out, it's usually not just that one bulb that fails. It's usually the entire length of it will fail after that bulb. That's because once that one bulb goes out, well, essentially, our circuit here is no longer complete. Because if we were to look at the side view of a light bulb here, essentially what we have is we have the wire coming in, it's then connecting here to the light bulb, and then continuing on like this. If we remove that light bulb, if we remove this bit here in the middle, now the circuit's no longer complete, electricity can no longer flow to it. So it dies. That's why Christmas lights especially will go out whenever one of the bulbs fails. And once you replace that one bulb, Oh, well, now everything afterwards will start working. All right, parallel circuits. So, parallel circuits, as I said before, are just circuits that are going to have separate parallel paths. Rather than everything being one after the other like this, if I just add in some resistors here, we'll do it like this. Instead of having them like this in little paths, they're going to instead be parallel to one another. Oh, come on. Does not want to advance. There we go. So instead of having it like that, now it's going to be parallel, as we see in this picture here. In terms of current, it's still the same. The current is going to be the same throughout, but it's changed slightly. Instead of having the current be the same here, here, and here, like we had before, it's a little bit different. The total that you begin with now, that we have over here at the start, right here, if we have, we'll say, again for simplicity, 3 amps of current in the beginning. Once we start going through that circuit, each of those paths is going to have to take some of the electricity. Again, going back to the water example, if you have a single pipe flowing, we'll have this right here, a single pipe flowing, it has a bunch of water in it here. Well, if this pipe then splits off into 2 other pipes this way going in separate directions, well, assuming that they're both level, where's that water going to go? We can't magically create more water, so instead of having essentially here 2 streams of water up this main pipe right here, now each one flowing out here is only going to have 1. It's going to split. We still have the same total amount of water, but now it's split off, it's reduced to go in each direction. It's the same thing with current in wires. Once we have these junctions, they're going to start splitting. So the current at point 1 here, plus the current at point 2 here, plus the current at point 3 here, all of these have to add up to whatever we started with. So if we started with 3, we have 3 separate paths. It would make sense that each of these would be 1 amp plus 1 amp. It does not want to write. Plus, okay, plus 1 amp. There we go. It adds up at each individual point. And it's the same thing here with resistors. If I get rid of this drawing here, current flowing in will split out between each way. It doesn't matter if we have these separate multiple junctions here, or if we just have a singular junction and it splits off in 3 ways, it behaves the same way. And that also means, if we again here, say we have 3 here, 3 amps at the beginning, once these all recombine here at the bottom, how much are we going to have at the bottom? We're also going to have the same amount. We're still going to have 3 amps here, because all 3 of those paths then recombine. So we will have the same current after any parallel parts of the circuit. They will recombine, and it will be the same as at the beginning. Here's another visual example of a parallel circuit. Instead of having them straight in a line, now they're separate parallel paths. Here's kind of an example of something that would be very simplified in your house. Most houses don't work off series circuits. The lights near one part of your house don't go dimmer when you add in another one. That's because we have them in parallel. So your dome light here would get the same amount of power as your headlights here, as a horn, as a motor, and as a radio. I'm sorry, this is not a house, this is a car. Oh my, it is early. Either way, same deal. Parts of your car and your house are usually hooked up in parallel, so they all get the same amount of power. Same amount of current going through them. Here's an example of the house. Each one of these outlets here is held up in parallel. They're all connected to the same wire splitting off. So each one of these here is in parallel. These are separate paths. They're all branching off of the same path. If we wanted to kind of flatten this out, if everything was in series, it would essentially look like this. We'd have a bulb here, and a bulb here. But instead what we have of having that, if we again flatten this out, is we have a part coming in that's splitting off in multiple parts here, separate junctions here, to provide each of these bulbs their own power, and then they'll all eventually come back and combine together in kind of a simplified view. This is more of like a schematic view. But this is what your house essentially looks like, very simplified. So again, the sum of the current in all the branches is going to equal the current of the main line, whatever you start with. Here's a quick animation to essentially show that the energy here, these little chickens we have here, are going to split up and go in different ways. It doesn't necessarily need to split cleanly like I had before. If we had 3, each of them would have 3. That's not necessarily always the case. Again, it depends on Ohm's law, V equals I R. It's going to depend on these resistors here, on the voltage, how much each load needs. So let's take a look at that now. So we're starting out with 5. We have 5 amps in the beginning. We'll have it start flowing a little bit. They flow along fine, all in one group, 5 amps, and we get to this junction. Now, depending on the load, it's going to split. So we can see here, 3 go down this main path here, and only 2 head this way. And then at the bottom, they recombine. So this one had 3, this one had 2. We get back to this closing junction. They go back together, and we have a current of 5 here. We started with 5. We have 5 down here at the end as well, as they make their way up to the battery. So just again, we have 5 in the beginning. We get to that junction. It will split depending on the load required. 3 on one, 2 on the other. And then they recombined. And then they flow back to the battery. So, now going to resistors. The way we calculate resistance is different for parallel circuits. Instead of just adding them one after the other, we now need to use the inverse of each resistance like this and add them up separately. This is just due to how the different parallel circuits work. It's a little above the scope of right now, especially since we're just doing this all digitally. It's going to be a lot harder to describe why some of these happen, but we're just going to have to kind of, for now, I'm not happy that I have to say this, we just kind of have to accept that this is how it works. In series, you add them up, just 1 plus 2 plus 3, add them together, get 5. When they are in parallel, you're going to do the inverse of them. 1 over 1 plus 1 over 2 plus 1 over 5, and then do some math. So, I want to make a point of that now, because you're going to have to do cross multiplication or be clever with your calculator to be able to figure out these answers. So, let's say I want to find the total resistance here. Let me just make sure. Okay. Let's say I want to find the total resistance. Let's say I have, like I said, 1 over 1 plus 1 over 2 plus, whoa, shouldn't be up there, plus 1 over 5, we'll say, equals 1 over R total. Oh, I'm going off the edge of the screen. So, easiest way to do this is just to use your calculator and make sure you're using your parentheses to figure these out. If you want to go through and make sure each one has the same common denominator, you can do that. Find the common denominator, modify all of them to be the same. Simplest way is just use your calculator. So I'm going to do that. So I'm going to do 1 divided by 1 in brackets, and I will show you how I'm entering this into my calculator. Using brackets, 1 divided by 1 plus 1 divided by 2 in brackets. It's very important you use these brackets here. I'm going to run out of room, so I'm going to do plus right here. 1 divided by 5 in brackets. Same deal. 1 divided by 5 in brackets. And this is going to give me a number. Here I'm going to get math. Let's put this into a fraction here. As a fraction here, I am getting, when I put this into a fraction, overall, I get 17 divided by 10. Okay? Or I get 1.7 if I just leave it as a number. But remember, this right here, and I'm going to erase some stuff on the other side here to make room, this is not my answer. This is what I essentially have. I have, and I can show it this way as well, I'll leave it as the number. We'll do that. actually. This gives me 1.7. That's not my answer. What I have is 1.7 equals 1 over R total. Not equals my resistance total, 1 over R total. So, you would have to essentially multiply both sides by RT to get RT on the top, because that's what we're looking for. So now I would have RT, R total, multiplied by 1.7 equals 1. And then I would divide 1.7 on each side to get it by itself. So what I would actually have is that R total equals 1 over 1.7. This is my answer here. It's not just what you get by just doing this part over here on the left. That's not the answer. You have to get the inverse of it. Multiply both sides by RT, or just do 1 divided by whatever answer you have. Okay? And then once I do this, 1 divided by 1.7, I get an actual answer up here of 0.58 is my total resistance. It's not a lot of resistance. So if I wanted to replace all 3 of those parallel resistors with just a single resistor, I would only need one of 0.58 ohms, even though I had one of 1, 2, and 5. The overall single resistance is going to be much lower. Okay? Am I forgetting anything? No. So, for those of you that do want a shorter way to do this, if you don't want to go through the process of multiplying, doing all that cross multiplying, there is a shortcut if you have a calculator. So in essence, 1 over x, or 1 over r in this case, is just the inverse of x. So if I just have 1.7, if you just take 1.7 and raise it to the negative 1 power, 1.7 to the power of negative 1, that's taking the inverse, and that gives us 0.58. Exactly what we had before. That's the shortcut version of this. Once you get this total resistance answer over here, raise it to the negative 1 if you are dealing with parallel resistors. Okay? That's the shortcut way to do this. Just raise it to the negative 1 power or raise it to the inverse. Either way. If you're more comfortable doing it the way where you do the cross multiplication, that you visualize it as 1.7 equals 1 over R total, if that's more comfortable to you, do that. If you can visualize this and just say, oh, hey, I just need to take the inverse of both sides and I'll get my answer, that's also fine. Either way. So, with voltages, same deal. The voltage at the start will be the same all throughout. And this is because, if we go back to that, essentially that potential energy, gravitational, instead of having this like staggered cliff drop like this, you're just going and doing multiple smaller cliff drops. So it ends up being the voltage drop at 1 is the same all across those parallel capacitors. Because instead of having this staggered cliff face here, we just have cliff after cliff after cliff like this. One single, essentially, height. That's just repeated. So if we have a voltage here of, let's say, we'll go back to 15, each one of these voltage drops is going to have a 15-volt drop across them, across all of them, because they're all parallel. It's the same height that they're dropping, essentially. This is where we start to get a little bit confusion, that there is differences between series and parallel, and you do need to be able to keep them straight. Which ones apply to series ones, which ones apply to parallel circuits. So when we're dealing with series ones, remember, if I go back to that, you have to add up. The voltage drop at the beginning has to equal the voltage drop across all of them. But when we're dealing with parallel, whatever the voltage drop in the beginning is, each one of those branches, voltage 1, voltage 2, and voltage 3 for each of those resistors, is the whatever you started with. In this case, 15. So each one would be 15. Moving on, some more bits about resistors in parallel that we have already talked about. So, this is why when you have things in parallel, your bulbs tend to be brighter. Because whatever voltage drop you have in the beginning is shared between each of those drops. So when we have two in series here in the beginning, well, they're both going to be kind of dim. But when we get over here to the first one with two resistors, here the bulb is going to be brighter. Why is that? Because if we have a 15 voltage drop across both of these, once we have that essentially reconnecting, this one here is having the 15 volt drop as well, if each of these is 15 here. That's that same reasoning here. Each one is getting the same amount of voltage to it. All those currents are recombining and going back to the beginning. Or not to the beginning, to the end of it. This is why we want to have things in parallel. Each one gets the same amount of voltage. And the same deal again, well, not same deal again. This time, when we only remove one of the bulbs, only that little part there dies, not the entire thing. Only this branch here is going to break, because it's not flowing into anything else, it's flowing back in. Once this one breaks, well, now we don't need to have any current going over here because it can't flow anywhere. So all the current would just go into these two separate branches here, thus conserving our total charge. Whatever current we have in the beginning has to be the same overall at the end. It doesn't just magically disappear and flow out of the circuit, it just won't flow. So, as I was saying, advantage of parallel circuits, one outlet can have something connected and turned on while another outlet has nothing turned on or connected. If they were all in series, once one of those outlets is turned off, the whole thing is going to shut down because current can't flow through it. Same deal with your light sockets. This is how they work. Each one gets that same voltage drop because they're connected to the same wire. They're all going to have those junctions. They're all going to have the same voltage drop. There are some disadvantages to it, though. When we have those multiple branches, there's going to be overall more current required to flow through the wires. Because each one's having an overall higher voltage drop, higher voltage means more current is required. This usually will lead to, if you overload circuits, I'm sure some of you have been told not to plug too many things into the wall, especially if you have those, essentially those, like not brake boxes, the extenders to add more slots in for your outlets. If you throw in too many things, if you plug too many things in, you're going to overload the wires, because remember, there's energy flowing through there. They're going to heat those wires up when we have current flowing through things. Those wires heat up, they melt off their coating, they touch wood, they set the wood on fire, now you have a house fire. This is the disadvantage to parallel circuits. But the advantage to them are so high, we just accept those risks and work in ways to prevent that from happening. Circuit breakers shutting off the entire circuit if it starts to get overloaded is one way to protect that. And again, just talking about the homes a little bit more. So short circuiting is essentially that. If you were to take, essentially we have a circuit here, and then just give it a better path to take, it's going to want to take that path. It's going to produce a lot of heat, and the current's going to be really high if there's a very low resistance. Though again, we don't talk about short circuits a whole bunch, but this is what kind of happens when if you have two parts of like an exposed wire and you connect them, similar to when I was talking about the toaster yesterday. If you were to touch part of that toaster with metal, you're going to short the circuit. You're going to give it essentially a path to get out faster, and the whole circuit will break. And just ways we protect against overloading, like I was saying, fuses and circuit breakers. These are kind of designed as like a fundamental portion that if too much current starts to flow, that specific part of the circuit will melt by design in such a way that it breaks the entire circuit, and now nothing can flow through the rest of that circuit if it's starting to get overloaded. This is what happens when the circuit breaker will flip. Or alternatively, instead of melting and breaking, it'll essentially activate a switch that will shut this entire circuit off as well. Same thing. The other one some of you might be familiar with, GFIs. A lot of appliances have these. They kind of work the same way, that if too much current starts to flow, it just flips a switch and shuts the entire thing off. They work in a very similar way. and that is all we have on circuitry. So, circuitry is difficult, and I know for a fact I'm not explaining this at 100% because I'm just kind of talking and I can't get any immediate feedback from you guys. If there is anything that you feel I didn't explain super well, please email me and let me know, and I can try to not reevaluate, but re-explain these things. Because I'm just here talking to my window. I might be talking too quick, I might be saying things and not saying them in the right way. Please let me know, okay? If you have any other questions, again, don't hesitate to email me. Otherwise, I hope all of you have a wonderful day.